So when we're graphing polynomials, it's going to be a rough sketch graph. Yes, ma'am? Nope. This will be total non-calculator. Okay. Oh, yeah. You're going to see this real quick here. I'm going to try and keep things curtailed to values that you don't have to worry to make it so difficult to do. There's no point in taking, something to the 8th power. We're going to keep things cubed, 5th power at the maximum, but we're only going to be looking at 2s. So it'll be stuff you'll be able to calculate in your head. Yes, ma'am?
So like the cube stuff isn't going to be on there?
You'll see in a second. Okay. It's everything we've done up to this point in polynomials. Yeah.
What do you mean by go to the next page?
Go to the next problem. This is what I'm saying here is that the steps in doing this, I'm making light of how simplistic this really is.
Oh, this says problem. Oh, I thought it said page.
So I'm going to start with just one quick, simple example to show you guys where we're at. F of x is x cubed minus 2. And we're going to graph that. Rough sketch graph of f of x equals x cubed minus 2. So now this goes back to the very first thing we're going to look at. The first thing you're going to do is identify what the tails are doing. What is the end behavior of this? So this is an odd exponent. First term's even, so everybody's already dancing. Which way is it going? We know that the tails of this problem are going to be going up here and down here. Okay? I don't know what it's doing in the middle, but I know at the ends it's going to do that. All right? So we've done that. The reason I put that on there first is because then when I go to make my table, I know to pick easy numbers to work with. And I'm always going to pick -2, -1, 0, 1, and 2. Yes, sir?
You mean like it was odd and positive?
Yes, sir. Okay. It was an odd exponent, positive first term. One of the things that I want you to think of, it's kind of a quick offshoot with the end behavior, because I know we tend to still have issue with that, is if you're looking at it as an odd exponent, even value, it's always going to be going up and to the right, increasing, going from left to right, correct? Wouldn't that be kind of the same idea? Wouldn't the slope of that be positive? If you break it down to something that you already know of, try to relate it to something you know, slope being positive goes up and to the right. Mx, bless you, mx plus b, that's a polynomial, isn't it? What's the degree of that polynomial? It's a first degree polynomial. It's got a slope of 1. It's going positive, it's up and to the right. If it's negative slope, what direction was going? Down and right. So if it was a negative value with an odd exponent, it would be going down and right.
So now you're relating curvy lines to straight lines.
Yes, sir.
Okay.
Because a straight line is still a polynomial.
Yeah, I got it.
It just has an exponent value of 1. Same thing when you think about your curves when you're looking at evens. I'll come back to this in a second. And when I have a parabola is an x squared one, correct? If the parabola was x squared and its first term was positive, it was up like a cup. Isn't every other even exponent mirror off that same tail then? The first term is positive and it's even, your tails are up. First term is positive, or excuse me, first term is negative and your exponents are even, tails are down. It mirrors the same thing as a quadrilateral does. Quadratic. Quadrilateral, I don't know what I'm thinking here. It mirrors the same thing. So if you can relate it back to a very simplistic polynomial looking at a line, mx plus b, or a quadratic, x squared. Every other polynomial with that same degree being odd or even matches the same stuff. It always will. Okay. So going back to that little table that I had going here, I'm just picking the easy numbers to work with. And these are things you should be able to do in your head. What's 2 cubed? What's 8 minus 2? Okay. What's 1 cubed? What's 1 minus 2? What's 0 cubed?
0.
What's 0 minus 1?
2.
Negative.
Sorry, minus 2. Sorry, negative 2. Negative 1 cubed. Negative 1. It's always going to be negative with an odd exponent if you give it a negative number. So I have negative 1 minus 2, you get? Negative 2 cubed gets me negative 8, and then subtract 2, you get? Negative 10. Okay? Notice I'm not picking really large numbers. I'm not making things, trying not to make things very difficult for myself. Using 2s, 1s, and 0s, positives and negatives, it's exactly what you need to do to plot these. You're getting the rough idea of what's happening around the origin. If you guys think back when you learn how to graph lines, isn't that those numbers, same numbers you picked also? Probably. Okay, probably. So if I go back into, like a rough idea here, negative 2. And 1 and 2. At negative 2, I'm at negative 10, so I'm way down here. So I'm my little tail over here a little bit. Okay. Negative 1, I'm at negative 3. Oops. Obviously. 0, negative 2. 1, negative 1. 2 and 6. I don't know, right here. It's making my curves. God bless you. I'm not overly concerned that my graph didn't match where my tails were placed. Placing the tails on the graph first is just helping me to know that when I do my substitution, I do those quick little addition parts in my head, that my signs don't get screwed up. Okay? I was helping someone just last hour in Flex that knew that what she had on her paper wasn't right because it wasn't matching what the tail ends were supposed to do. And she couldn't figure out what she had messed up. Well, she had messed up on one of the values. When she squared something in her head, she thought negative 2 times negative 2 was negative 4. It was just that simple to do. But knowing how the tails work will help you to avoid making that simple mistake. All right. Does that make sense? Same idea as we get into some of the larger degree polynomials. If I'm looking at f of x is negative. Here's how I want you to write this. Anytime you have a first term that's negative, and it's not like negative 2 or negative 3, if it's just a negative symbol, do me a favor. When you write this down, put negative 1 in parentheses, x to the 5th, x squared plus 1. Write it like that. Make sure you put that negative 1 within the parentheses. What that allows you guys to do is that it'll force you to remember what you're doing when you substitute in. It'll force you with your order of operations not to make 2 negative. And I'll show you here in a second.
I use the x, negative x to the first power instead of negative 1 times.
Well, I'll show you in a second here. You'll pick up on it real quick. First of all, tails. What are my tails doing? It's like a negative slope, right? Are we okay with that? Okay. I know my tails are going to have some sort of, I know they're going to look like that. There's going to be a lot of other junk going on in between, but I know what the ends are going to look like. I know what 0 is. Okay. Here's the reason why I was telling you guys to put that negative 1 in parentheses. When I write it out, negative 1 times negative 2 to the 5th plus negative 2 squared plus 1. 2 to the 5th is about the largest value I expect you guys to be able to do in your head. Because what's 2 cubed? 2 to the 4th, that is. 2 to the 5th is 32. You should be able to crank that out. Okay? 2 to the 5th is something very simple to raise to an exponent. I won't make you do that with 3's because after 3 to the 4th power is 81, Okay, maybe if you do 3, so it's 243, so it's not that bad.
So-
More often than not, it's just going to be 2s would be the largest value I'd ever expect you guys to be able to raise to a higher exponent. Not 5s, 6s, anything like that. It gets to be too
Well,
much.
if we do multiplication on the paper, we can figure out the square.
You could do that, yeah, but it's, I want this to be a little bit more mental than it is cranking it out like that. Now, what, do you guys remember what the rule is if you have an even number to an odd exponent? Will it be, or sorry, not even, an odd number to an odd,
No.
Negative.
thank you, negative. I would get it right eventually. If I have a negative number to an odd exponent, will the value be positive or negative? Negative, okay. So I get negative 32. What's negative 32 times negative 1? 32. Positive. So I have 32 plus 4 plus 1. 37. And that's helpful to know that it winds up being positive because it makes sense because at negative 2, it's already way up here. Where's my tail pointing? My tail's pointing up that
So
direction.
is negative 1 to 3?
The next one would be, yeah, negative 1 times negative 1 to the 5th plus negative 1 squared plus 1, whatever that is. So negative 1 to the 5th, negative 1, times negative 1, 1. So I have 1 plus 1 plus 1, which is 3.
Price. That's a big jump.
Bless you.
Isn't it?
It's one of those weird things. You have to start to realize that these exponent values are going to make these things messy really quick. Okay. Now we have negative 1. There's 1 to the 5th plus 1 squared plus 1 should equal 2.
Yeah, sure.
Oh, yeah, sorry. I'm sorry. Yeah, so it's negative 1, 1, and 1. Thank you. Sorry about that.
Then it's in the same place as the 0.
Well, what's between 0 and 1?
Huh?
There's still numbers in between, right?
Yeah.
So it's like chocolate's 20.
Okay, we're just getting a rough idea here. It's, okay. And then I use 2 again. So we have negative 32 plus 4 plus 1.
Negative 27.
So as I'm going through these things, at 1 it was at 3. Or excuse me, negative 1 is at 3. At 0 it was at 1. At 1 it was also at 1. But then at 2 it drops way down here again. As we get further along into polynomials, you're going to have what are called points of inflection, places that it changes direction. Okay? In this case, it's a 5th degree polynomial. When it's a 5th degree polynomial, that means it could have up to 1 less than the degree amount of times it changes direction. So a 5th degree polynomial could change direction in the graph 4 times. Okay? Sometimes it does, sometimes it doesn't, depending upon all the other extra values are. So if I go to rough sketch this, I know that it's decreasing. And it's doing something like that. It's got to have some stuff in there. Okay? It's that rough idea of where it's looking at. Now, I know that we've done, what do you call it? The quadratic where it just looks like, where a 4th degree polynomial just goes up and down. Sometimes the 4th degree can do this as well. Okay? It just really depends upon the problem. Yes, ma'am?
In the little section, like where the 1 and like 0 and 1 and 1 and 1, will it ever go up? Like will it ever go like that?
There are points within here that it's going the direction. I mean, this could even changed it here and going through. Okay, this could have come down. It could have gone up, come down, and gone up. There could be those little ridges and stuff in there, but excuse me, we're not at the point yet where we're looking at the localized area. Clay, you were talking about this the other day about the interval. Remember we had the interval like between 0 and 10? that word problem.
Greater than and less than.
We were looking for an interval space. We're not at that point yet to get into this specific interval of what is going on in there yet. We will eventually. And when we get to that weirdness part, the calculators will be back in your hand and we'll do a lot of stuff via the calculator. Okay. For us, we're looking at tails, general shape, and we're fine. Okay. Not so bad. Alright. You know. Not yet. We'll get there. This is just 3x. This bar thing isn't here, so don't. It just showed up. Why don't you guys try that? Okay. Okay. You guys try that. Are you guys using the trick of thinking about it being an odd exponent and going via slopes?
Yes.
So it's going like this?
Yeah, that's what I do.
That's fine.
I do what I do.
So I know it's going to have to go. Woo-hoo. So you have -1 times -8 minus 6. 2?
Yep.
-1 times -1 minus 3. -2?
Yes, ma'am.
0.
0.
Got that one right.
-1 is 1 plus 3.
That doesn't make any sense. Just you watch.
Theta
You
1.
learn this. Just remember, it's one less than the exponent, so it can change the direction twice.
Up to 2 times.
It can change it twice.
It could, yeah, all right, I didn't hear you say it could, so yeah. So you have -8 plus 6, -2.
I like these. These are something. Just get to the harder ones.
So, like Clay was saying, it's a third-degree polynomial, which means it could change direction up to 2 times. It just so happens that we were able to identify localized maximums and minimums. These values here, this actually does become your localized maximum and minimum here. That's what you would call a point of inflection. In your calculator, you could figure out a maximum and a minimum of a specific boundary. You know how in your calculator it asks you for left bound and right bound?
No.
You'd set your left bound here, your right bound here. It would search within those parameters to find this ordered pair. And that's kind of what we were doing on the interval. This is looking at a specific interval chunk of a polynomial. That's all that
We
is.
can do things faster in the calculator now,
We'll get there.
because that's what we're doing right now. It seems like a pain to do on the calculator.
You're right. Oh, yes. I thought you were asking, we will be able to do. No, this is so much faster to do by hand. You're just looking at a generalization of where you're at here, okay? Not always will this point be evident that you'll be able to get that exact value. I mean, it sometimes doesn't work that clean, all right? So let me show you the other style of these. If you actually were working with these yesterday, and what you guys were doing was multiplying these out. What I want to do is rewrite this problem into a function notation. What I'm doing here is I'm rewriting it as f of x equals these 3 terms.
I got you.
These 3 terms mirror the idea of when we had it like this. And we called that intercept form. Remember that? With the quadratic, we found that as the intercept form, and you could have told me where my 2 zeros were placed, correct? We found an axis of symmetry and went for it. Now, when you have a polynomial, you won't necessarily have a specific axis of symmetry, but this is still written in a form of intercept. In here, we could find our zeros. What makes that function equal to 0? And all you have to do is set each of those 3 terms equal to 0. So when you go to graph it, you can tell me my 3 zeros.
-9.
Negative 9.
7.
So -9, 2, and 7. Now, if you were to multiply these out, would this leading term be positive or negative? It's going to be positive. The leading term will be positive because all three of the x values are positive. What's the degree? It's a cube, so it's a positive first term, odd power. What direction is it going?
That way, yeah.
I know it's got to do that. Now I put my zeros in. 9, 2, 7. Increasing, changing, going back up. I don't know exactly where those curves are shifted. I don't know how high up it goes. I don't know if it's scrunched in a little bit, no. I don't know if it's increases that quickly or whatever. But all I know is that it's got to be increasing, decreasing, and increasing because it has to go through the x-axis 3 times. We're not necessarily trying to identify what these localized maximums or a minimum is because I'm not letting you use your calculator to do that. Okay? We're not worried about that yet. Yes, ma'am?
How did you know it wasn't like?
If you multiply these out, would you agree that you wind up with like x squared? And then if you distribute again, you get an x cubed? Would that first term be positive?
Yeah.
That's how I'm doing it. Yes, ma'am?
So all we have to do is vectors and then
That's all it is. That's really all it is. Yeah.
Can that first arc connect from higher?
It very well could be. I have no idea what it looks like. No. I'm just doing a visualization of not drawn to scale. Okay? I have no idea what it looks like. All I know is that my zeros are placed there.
We could find it by taking like the difference between -9 and 2, right? We could find the x symmetry for that.
We could do a bunch of things. I'm not worried. I'm not.
We can find it, right?
We're getting there. We're not there yet. Not even close.
I like jumping forward.
All right.
I like jumping back. Are you doing another one of those?
Yeah. Well, we're gonna do this one a little bit crazier.
Right easy now.
Yeah.
Still gonna be cute.
Oh, he's getting fancy.
I got fancy on you.
Really, sir.
Oh, stop this.
It's gonna cross the
-3. Then this is x to the 4th.
Now, you guys have already jumped ahead here. There's 4 terms. We know it's going to be a 3 polynomial.
True.
If I multiplied all those x values out, would that first term be positive or negative? It'd be positive because each and every one of those x values is positive. Now, just hypothetically speaking, what if I did that? Then it would be negative. What if I did this?
Positive.
Negative. Positive. You make me smile. That's the only time we can say something nice about you. The rest of the time, you guys all smell funny. So we know it's an even exponent.
That was a low
First-
blow, bro.
You live on a farm, so it's just natural.
That's insane.
So I'm sorry, that was too easy. I apologize. We know our tails are going to be pointed up. Everybody okay with that? Okay. We also know that our zeros are at -3,
4, 5, -6.
4, 5.
That's -6.
Even exponent, positive first term. I have 4 zeros.
W for win.
It'll look something like, I don't know what it looks like, but it should look something like that. Now, if you put that in your calculator, you'll see it. You'll see that you might have to mess around with your scale and all that stuff, but it would still mirror the idea of your first term is positive, you have an even exponent, so you're going to be, your tails are pointed up. You'll notice that you have zeros placed on those, but it's just the scale of your f of x, who knows where that's at.
Figured out how to spell my name in the calculator by graphing. Wait, could you really do that?
That's an M.
What was the problem again? X.
X plus 3.
Hold on. X plus 3.
X minus 4. X minus 5.
I already.
And then X plus
This
6.
is how it changes. I've been trying to find this. Where is it?
I'm just showing you what it looks like.
X
Jeez.
plus 6.
Wow. Vicious around here.
I need your calculator back. Because you can.
I am.
Oh, they're not.
My scale is just a little off, but
Not convertible today.
Why is your Y name at 1,000?
just trying to get an idea of it. So yeah, you got the general idea of where it looks like. This is what I want you guys to be able to accomplish from today, is just get a rough sketch idea. It bases itself off of your end behavior, being able to substitute in some very simple ideas, or using what we're going to call an intercept form for the polynomial. It'll work very clean.
I got you.
Okay? Questions at all? Sir?
Stuff like this.
Yeah, I'm going to mix them both together. What I'm going to do here is I'm going to build it out of the 6 sections that for the past 2 days. It's on so it's on section 6.2, which is page. And then section. Oh, this is the wrong page number. I'm looking at the wrong post-it note. Someone took my post-it note. Sorry.
Give me a value. Because you didn't put it in Y. Why do you put it? No, but it gave you.
What I'm doing here are these problems on page 342. Those were the ones that you guys just had to multiply out. They gave you 3 terms. What I'm asking you to do is rewrite them how we just did a second ago. We put f of x in front of those 3 terms. We're basically creating our own intercept form of polynomial. That's all.
That is 49 to 52.
Yeah, that second group that we did. Yeah, was where you just found the zeros. So when you write those out, just put f of x in front of those 3 terms, and then go from there. Okay? And we're just going to talk. Make sure you just start with your end behavior, plot your zeros. Here we go. It's been one of those long days.
Oh, no, like just today. Somewhere. And behavior. The biggest exponent is